cannot carry things more than I do. Okay. What did we learn last time about asphalt binder? What was the most important factor to consider if you want to design flexible pavement or asphalt pavement for a location, for a job site? Do you remember? Yes. The temperature, the climate. Remember this picture where you had Toronto and then on the other side some really paradise island, and you cannot have the same asphalt to use for both. So we need to have a way to choose the right asphalt. And in the past, there were different kinds of grading. As you can see, items 1 to 3. But the one that we are using is performance grading. And it is called PG. And this is what we want to start off with. And this performance grading is relevant to the modern pavement design strategy, which is called Superpave, an abbreviation somewhat of superior performing asphalt pavement. And this is relatively recent, and it considers the performance of asphalt considering the 3 major deterioration mechanisms that we talked about last time. Do you remember those? The 3 different problems asphalt pavement could have? The 3 pictures with cracks. One was rotting, which happens when the asphalt has low viscosity in high temperature. So you are going to have these hills and valleys. What are the other 2? Someone else. Thermal cracking, low temperature cracking, excellent. That's kind of the opposite. When you have high viscosity and cold climate. And the third one, fatigue cracking, which was a mapped cracking under wheel path just because of a lot of traffic. Okay, great. So we are in a good place to go ahead with this. So what you want to design is to prevent fatigue cracking, low temperature cracking, excessive aging. We talked about aging last time too. Do you remember what aging means for asphalt? What happens over time? Becomes more brittle because what material property is changing dominantly? Viscosity. Just like human beings, asphalt becomes stiffer as it ages. So basically, what you want to do is grade the asphalt considering the temperature with regard to all of these properties. It turns out that it's very simple, but you need to pay attention. The name starts always with PG, performance graded, and then there are 2 numbers. The one in the beginning tells you the maximum temperature you can use this, and the second one, including the negative sign, is the cold temperature. And the high temperature is measured a little bit below the pavement surface, and the cold temperature is measured on the surface. So when you are talking about asphalt PG 5228, that is an asphalt which is good to be used from negative 28 degrees centigrade to 52 degrees centigrade. You may think this is very high, but the temperature of the pavement is different from temperature of the air. It can be much higher than the air temperature and much lower than the air temperature. Sometimes you see signs like bridge can be icy. Have you seen that? I mean, PA, we see it often. It's when you have a bridge, there is nothing underneath, and the asphalt, the material can be much colder than what you think it is, and it can be icy. So, pretty simple. You have the high temperature and low temperature. So if you are talking about 70-10, This is good from negative 10 degrees to 70 degrees centigrade. And the catch is you don't have material for every temperature that you have. So you need to use one of these materials. You cannot just use any, you cannot just have your own grading. PG, I don't know, 53 here, negative 21. It doesn't exist. So you need to learn how to choose the right material. And also, and this is kind of the same table in a different format. So these are the ones we have available. A little bit like a steel, you cannot just, make your own asphalt binder. You need to choose one of these. And there is another catch. If you have the maximum and minimum temperature, as you can see, living in a state college, things can be very variable, right? You don't have a maximum temperature of, look, it's April, and this morning was very cold, in my point of view. So you can have you have a distribution of temperature, and you have a distribution of cold and high temperature. So if you just go with the average, then it's only 50% reliability. Let's do this exercise together. This is an example. The mean temperature is 56, and the mean low temperature is negative 23. So 56 and 23. What material do you use? We go back to the table. We look at 56, there is none. 23, also there is none. What do I do? As engineers, we always need to be conservative, okay? So if you don't find 56, what would you choose? That's not conservative, Dimitri. If it works for 52, it doesn't work for 56, right? This is the maximum. That's a good thing to remember. What do we use? 58, right? So we have to use this. And the other one was negative 23, right? Yeah. So now I have to look in this row. Which one do I use now? Exactly. Looks very simple, right? So you go back and say, okay, if you just want to have 50% reliability, you just use 58, 28. Why do I say 50% reliability? Because if you consider normal distribution, and you are just considering the mean values, half of the time this is not going to be the good answer for your climate. So that's something we don't like. You want to have something which has better reliability. Just like in concrete, where we were adding this 1.34 times a standard deviation for a strength. So what you do is typically you also know, you know this from the seasonal data, that what is the standard deviation, right? It can be broader or narrower. So you add, you say, okay, my maximum temperature is 56. Now for 90% reliability, you say my maximum temperature is 56. I add to that 2 times the standard deviation. I use sigma. You can use S if you like. And here is given as 2 degrees centigrade. So this will be 60. So I add to a standard deviation so that my material would work, even if things are changing dramatically. And then for minimum temperature, what do you think we do? Add 2 times the standard deviation or subtract? Subtract, exactly. Perfect. This is 4 degrees, so you subtract. And now you go back to the table. Go back to the table and find the grading again. The same numbers may not be available anymore. So you need to again be conservative. 60, negative 31. I go back to the table. Oops, we don't have 60. What do we have?
64.
Right. And we don't have negative 31, but we have negative 34. So the grading would be PG 64, 34. In the homework problems, there are examples like that. It's very simple. All you need to have that table and just to be careful and not make mistakes. Okay? Any questions about this? Everyone is comfortable why we are adding, subtracting, standard deviation? Why? Okay. Fantastic. This is what I explained to you. And if you want to see how a Superpave binder specification form looks like, it looks like that. So on the top, you see like the performance grading, 7-day maximum temperature, then minimum pavement temperature. But there are some other properties. And you have to ensure that, for example, the flash point temperature that I'll tell you today what this is, what is the minimum, or what is the viscosity measured at a certain temperature, and dynamic shear modulus, which we want to see what each one of these are. So it's interesting, instead of you finding the values, you actually have to target a certain value, and you have to see at what range of temperature it occurs. So temperature is like the most important thing here. Like always you see temperature playing a role because the material is viscoelastic and temperature changes the viscosity dramatically. So this is not very important. This is how to get the temperature maximum and minimum if you don't know the pavement temperature from the temperature of the air. Very quickly, I want to go through a few tests which gives us these parameters that we need for Superpave design. One is viscometer. I hope you remember this a little bit, rheometer or viscometer from early on this semester. This measures viscosity. Viscosity is everything for asphalt. You want to know how it changes with temperature, and it's also important for construction. So this test measures viscosity. It's kind of obvious, right? There are some other tests. One is RTFO test, rolling thin film oven test. This tries to simulate the short-term aging. Do you remember this graph? Last time I had a graph for you where we have here viscosity versus time. And then 3 phases. At tank, construction, and afterwards. Do you want to try to draw it for yourself out of your memory? Download it from what you remember from Wednesday and see if you can draw it. And then I draw it for you. Aging of asphalt. Viscosity changes with time. How did it go? Let me see a few triangles. I know you have it in your notes. It's okay if you don't remember. I'm just curious how many of you remember. I know you have a lot of different classes, you don't need to remember everything. But in the beginning, in the tank, nothing happens. When the material gets exposed to high temperature and air and pressure during construction, phase 2, the viscosity jumps up quite a bit. And then during the lifetime, it's kind of more asymptotic. It's increasing, but not at a very high rate. This would be phase 3. That's aging of asphalt. So what you try to do in these tests, you try to simulate this short-term and the long-term aging. So short-term means what happens during construction, and long-term is what happens during the lifetime, the service life of the pavement. So what do? You pour the material into some tubes, heat it up quite a bit, and then you expose it to air for 75 minutes. And this is kind of an accelerated aging. You want to see what happens to viscosity, and then you measure viscosity afterwards. Once you do that, this RTFO test, this is also in your homework. You need to kind of explain what it does and so on, if you have checked out the homework. Once you do that, you also have another test where you try to simulate this long-term behavior, because essentially you want to know as a designer, during the service life of the pavement, how the properties are going to change. You want to have good material that lasts for a long time. So that's kind of the idea. And here you apply pressure and temperature, and you look at viscosity before and after, pretty much. So this is more for long-term aging. And of course, we need to know the shear modulus and viscosity. I hope you remember that we had different ways to measure it. This is another kind of rheometer that you put the asphalt between one plate, which is stationary, the other one is rotating on the top. And then you do this at different temperature, and you do it on the age samples too. And this is going to help you, for example, to predict rotting. If shear modulus is very low, material is very easy to move, and then you are going to have a lot of rotting. I don't go to a lot of details of any of that, but it's kind of that you have an idea of what is going on. There are more details in the book if you are interested. And there is another test which is looking at low temperature cracking. We saw that this is one of the things we are interested in. This is a very elaborate test, very hard to do. If you ever do an internship for PennDOT or you have to do any of this, it's very hard to do. And you need to put the beam inside water, and you actually do 3-point bending. So you have two supports and a load, and then at a certain temperature, and you basically look at the strain, how it behaves. This is also done after the material is aged. It's a very hard test to do. And finally, the flash point test. This is pretty much for safety. You want to know at what temperature the material becomes flammable. So you basically increase the temperature and try to see when it starts to be flammable. Pretty much for safety, it's a very easy test to do actually, very easy. Any questions about any of that? So this is a summary that, especially for Monday, for example, when you want to review, make sure that you could answer, you remember what asphalt binder is, emulsion, last time we talked about cutback, deterioration processes, what's the difference between tar and asphalt, and then the things we talked about today also, the viscosity, how it changes with aging, how they are related to these deterioration processes. This is very important. And of course, you need to know how to do performance grading. Look at the homework problems. I suggest you to do that. And here is the list of some of the parameters. Okay, so now we can switch to the new handout. If you didn't pick up one, take a breath and get ready for this. Now, before we can talk about hot mix asphalt design, we need to learn a little bit how to calculate some of the parameters. So this is kind of comes in parentheses between just asphalt and hot mix asphalt. And I've printed this separately because, as you can see, this is 2 slides per page because you need to do a lot of calculations. I thought maybe 3 per page is too small. I know you are young, but still. Okay. So this is volumetric calculations. That means that we need to kind of look to see what phases are in the material, similar to concrete a little bit. And we need to be able to calculate mass and volume. And we need to learn about the specific gravities which relate always mass to volume. So we have these 3 phases in asphalt: air, asphalt binder, and aggregates. Everyone has this written down? Now, if you look at how basically things are inside asphalt, we have air voids. There are some voids inside the aggregates. We consider them to be a part of the aggregate. What is important is this absorb versus effective binder. Everywhere else in this chapter, wherever you see the word, the subscript E, this is effective, A is absorbed. Binder is B, so you see like BE, BA. And I hope the illustration is clear enough, but basically what is going into the pores and it's not available to bind things together is absorbed. What is kind of on the surface of the aggregates which helps things to glue together is effective. Look at the picture. I've made it such that hopefully it tells you what the story is. What's the difference? Okay. Any questions about this? Now, if you are doing soil mechanics, maybe you are familiar with diagrams like that. Maybe. I don't know how each person teaches. So people have different styles, but you may be familiar with diagrams like this. Then on one side we have mass, on the other side volume. And what connects them together, remember, it's always some sort of density. That's kind of what we know. And look at the notation. So BE, BA, and then MS, VS. And then the total is V sub T. For the mass, the same. And some of the obvious things that we can see here are, for example, the absorbed binder is kind of, if you remember the picture, it's a part of the volume of aggregates. And the mass of the binder is, of course, the mass of the absorbed and effective. Total mass is mass of the binder plus mass of the solid, which you can write MB as the summation, so you have this total. These are kind of obvious. Volume of binder is the volume of the two types of binders. Total volume is everything summed up. And you can write it in different ways. Right here, you take into account that volume of aggregates includes absorbed binder. Okay, kind of obvious. So, there are some definitions. Important. Binder content. Mass of the binder over the total mass expressed in percent. The rest is mass of solids or stone, M sub S. So you see, you can just say MS over MT, or one would be 1 minus the other one. Yeah, because the summation is basically the whole material, right? What does this remind you of? Dividing two masses in concrete? Moisture content, exactly. It should remind you of kind of moisture content. Here you don't have moisture, you have binder content. So you divide two masses. Simple. And there are a number of different air void contents in asphalt concrete technology. The most obvious one is air content. This is kind of another word, another term for that is VTM, voids in total mix. Voids in total mix. And air content, I hope you remember from concrete also that it's kind of always based on volume because air doesn't have a mass. Simple reason. And this is just the volume of air over the total volume. But this is not the only air content that we need to learn. Everyone has this written down. So far we learned about binder content. This is mass related. Of course, the rest would be mass, stone content, 1 minus binder content, obvious. And then air content, VTM. There is another one, VMA. This is voids in mineral aggregates. And here you add the effective binder volume to the volume of air. It's a definition. So this is VMA. So if there was no binder, you could think of this as the air content, if there was no binder. There is a third one, this is the last one. Voids filled with asphalt. This it has nothing to do with the volume of the asphalt. It tells you how much voids you have in the voids, basically. VFA, filled with asphalt. How much is filled with binder? So if you have no air content, then that would mean that this is 100%. That all the voids are filled with binder. Everything you have is binder. I want to wait for everyone to write this down. So these are definitions that engineers have found to be useful. Different types of air voids. And then there are specific gravities. But don't worry, you don't need to memorize them. You can always have them on your formula sheet. So this is kind of putting everything together. It's good to have them all somewhere written up. Also for you to remember what everyone is. It's just a summary of kind of having everything together. Okay. Now specific gravity. So we have a bulk specific gravity. This is just for aggregates. So that's why you have S here. So when we have S, this is referring to solid or a stone, depending on, it can be also, some people like to say it's a stone. And then you have bulk. So B is for bulk here. Versus effective. So bulk, you count in the absorbed binder volume in. In the effective, you don't. So that's the only difference. Mass of solids, that's obvious, just mass of the aggregates. Over the volume, in the bulk, you count in the absorbed binder. In the effective, you don't. It's just divided by the volume of solids. Everyone has written down. Is there anyone who's still writing? And the last ones are a specific gravity now for the asphalt mixture. So this is not just for the aggregate alone, it's for the mixture. And mixture is, you see the M here, that's mixture. And B is again bulk, and M is maximum. And bulk is kind of okay, the mass of solids plus mass of binder, basically total mass over total volume. That makes sense. It's a specific gravity, so we divide this by the density of water. I forgot to mention that in the previous one. And the maximum means that exactly the same thing, only if you had no air, that would be the very maximum specific gravity you will have for your mixture. Okay. Wait. Okay. Okay. How do we measure, let's say, the bulk, a specific gravity of the mixture? The point is, for that you would use a compacted asphalt sample, so it looks like that. After compaction, you make a sample, and the way you measure it is actually similar to what we talked about in aggregates. So you use the dry mass, and SSD mass means you put it into water and make sure that it gets saturated, and buoyant mass. So if you measure these three, then this is how in the lab you would measure the bulk specific gravity of the mix. For measuring the maximum specific gravity of the mix, you cannot use, you have to basically take all the air out, and the only way to do that is to basically use the powder. You cannot use the sample anymore, so you actually use, you crush it, and this is what you would use, because you don't want any air in it. And then you have dry mass and buoyant mass. That's how you would measure it in the lab. Okay, now with all these definitions and formulas, we are ready to actually do some calculations. It turns out that there are some relationships between the air contents that you learned and the different specific gravities or the other parameters like binder content. Just for an exercise, I want us to show that one of these is true. So this is like an exercise. We look back at the definition of each one, and you try to show that, for example, this relationship holds. This is very useful when you design and generate these relationships, but it's important to see where they are coming from. So let's show that together. Start from the right-hand side, write the definitions, simplify it, and see if you can get to the left-hand side. Look back at the definitions, the names. I know you guys are very busy this week. Just use the time you have in the class to learn a few things that you don't have to learn back in your dorm. Start from the right-hand side. And then simplify it to get to the left-hand side. popcorn with the extra thing. Yeah? There should be some residual somewhere. Everyone should try to pick up. On the other one. So the definitions for G and B, which is a specific gravity, the bulk specific gravity of the mix, and the bulk specific gravity of the solid. So the way I have done it, I first looked how G and B over GSB will look like, just substituting. If you have done it differently, don't change it. Most important thing is that at the end, you get to the right answer. And this is the total volume, this is the total mass. You can kind of see where it is going. So this is, so that's why and now it's kind of easy to see. If you multiply it by P sub S, always when you have something like that, you should start from the side where you have more parameters, and then you simplify it towards the side which you have fewer parameters. So there is no one who hasn't picked up the pop quiz. Okay, so example one. So in your homework there are two problems which are require these volumetric calculations. The first one, you have a dry mass is given, you have the binder content, and you want to calculate VTM. And the other parameters are also given. So GB is a specific gravity of the binder. So it's just the mass of the binder over its volume. So one way is to use one of the formulas that one of these relationships that we proved one of them right now. Try to see which one you could use here. For example, there is a relationship for VTM. So one way is to use this relationship if you know it. You can also do it without. So that's why approach number one is to use this relationship. And if you look back, there is also a relationship for the GMM, which we are not given. So knowing these two, it should be very easy to get VTM. We know. If you read the problem, it's given. So I stop here. And these are, please come to the class on Monday prepared so we can start right away.